Okay, in this video I just want to go over the answers to the practice problems. All right, in the first question, which is correct for a reaction with a positive change in the Gibbs free energy delta G at standard state? All right, so remember, if you had a positive change for delta G at the standard state, remember what that would mean. Positive changes indicate that the reverse reaction is favorable. All right, so and also remember what it means to be at standard conditions. That means that this is going to be where all of the things have reactants and products have a concentration of 1 molar. All right, so that should have a capital M after it. All right, so a way to think about this is just saying, all right, where we're at when this thing right here is measured would be somewhere like essentially halfway between all reactants and all products. All right, and ask yourself, what would be true about it if when it's at that situation, it would want to move towards the reverse direction, all right, to the left, all right. Well, that would mean that the equilibrium position is somewhere between the middle and the left side. So it would be something like this, all right. So what's that going to mean? That would mean that in order to get from where it is, which is the standard conditions, to the equilibrium, it would have to move to the left. All right, so that would mean that the formation of reactants is favored. So the answer to that is A. All right, so all right. So the next problem, it should be fairly straightforward and just a matter of recognizing the correct equation to use. All right, this is it provides you with the standard state delta G, and gives you this value. It gives you this temperature. And we have this expression right here, delta G, it's under standard conditions, equals negative RT ln of K. We can rearrange this to give ln of K by itself, and we would end up getting this answer right here. And one last thing that I'm not showing here, this right here would be the value for the ln of K, or the natural log of K. And so to get K by itself, we need to do E raised to this value right here. And if you do that, the answer would be 0.0176. All right, let me just confirm that that is correct. And yes, so the answer is 0.0176. All right, to that exact number of sig figs. Okay, one thing that I wanted to point out about this problem here is just to make sure that your units agree. All right, the question gives you this delta G in kilojoules per mole. All right, so when we put that in, we've got that in kilojoules, but notice that our R value is 8.31. That's in units of joules per Kelvin per mole. All right, so we need to convert something so that our units are going to agree. And down here, I showed that conversion. So if we had 10 kilojoules, well, a kilojoule is the same thing as 1,000 joules. And so that works out to be 10,000 joules per mole. All right. But one thing that you're going to make sure you do is to keep track of your significant figures. All right. This right here has got 3 significant figures. And remember, whenever you're doing a conversion, there's essentially an unlimited number of significant figures, all right? Because this is the same thing as saying 1.00000, infinite number of zeros, kilojoules equals 1,000.0000, infinite number of 0 joules, all right? It's an exact conversion, all right? So when you multiply that by this right here, we need to keep the same number of significant figures that are in this value right here, all right? So a way to indicate that is by putting a little bar after that third 0 to indicate that this would be significant out to that position. All right, so notice that's how I put that in there, so that your answer ends up having those 3 significant figures. All right, the next question just gets to, what are the conditions that we're going to have at equilibrium. Anytime you have a question like this, a lot of times I like to go through, so here they're asking you to get both situations correct. I just like to either put a check by the things that are correct for this, put a check by the things that are correct for this, and then the answer is going to be the thing where both of them are correct. All right. In the next problem, this is a standard equilibrium type of problem. Notice that in this question, they say it's placed in a 1 decimeter cubed reaction flask. All right, and when you look at that, remember that 1 dm cubed is the same thing as 1 liter, and that makes this very easy because it means that all of these mole values are going to be equivalent to the concentrations, or the molar concentrations. All right, and that's one thing that I've noticed, is that in a lot of the problems from the IB question bank, they do a lot of things per 1 liter. All right, and that just keeps the math pretty simple. All right, so this, we can write an expression for the equilibrium constant. We can also write the reaction here. We've got start, change, and finish. All right, and so one thing that it gives us is that the final value is going to be of nitrogen is going to be this right here. So I wrote that. We know that the change, because of the coefficients in this reaction, are going to be minus x, minus 3x, and plus 2x. Actually, at the beginning, we don't know whether it's minus x or plus x, because we don't know which way the equilibrium would go after this initial set of conditions. But one thing that we can do to figure out which way it's going to go is look at, well, what happens to it between the start and the finish. And we can see that it goes down. All right, and what that indicates is that since it goes down, that means it has to go towards the right, all right, for that to happen. So that confirms that this is minus x, minus 3x, and plus 2x, all right. If the reaction were to go to the left, you could just say that this would be plus x, plus 3x, and then minus 2x, all right. So since we know that that occurs, that means that we know that our x is 0.2, because that's the difference between these, all right. So we could figure out that 3x is 0.6, we could figure out that 2x is 0.4, and we could end up just saying, well, if this goes down by 0.6, it's going to be 0.4. Same type of situation over here, and then find the results that would be consistent with that. All right. Why is it considered homogeneous? Everything's a gas. All right. If everything in it is in the exact same state or same phase, it would be homogeneous. All right. Predict giving your reason the sign of the standard entropy change in the forward reaction. All right, so this gets back to like the types of things that would be consistent with a change in entropy. All right, so one thing, if you remember from talking about entropy last year, is that whenever you go from fewer particles to more particles, that's an increase in disorder. All right, if you ever go from more particles to fewer particles, that's a decrease in the disorder. All right, so if you take a look at this reaction, and notice I'm drawing it here as just the forward reaction. All right, this if you count up the total number of particles over here, that's 3 total gas particles, 2 from this guy and 1 molecule here. But there's only 2 total gas particles on the right side. And so that's 3 particles becoming 2 particles. That's a decrease in the disorder. All right, so that's a decrease in the entropy. And anytime you have a decrease in the entropy, that would be considered a delta S being negative. All right. Okay. So in the next problem here, it is it's a straightforward calculation using the this equation right here. One thing just to point out about this reaction here is that when they give the temperature, or sorry, when they give the equilibrium constant in the very beginning, notice the way they report that. It only has 2 significant, this would only be considered to have 2 significant figures. Therefore, that's going to end up governing the number of significant figures in the final answer. All right, so any of these values right here would be considered correct. Make sure when you give your answer here that you give units, all right, because depending on whether you're giving it in kilojoules or joules, it could totally change the value. So my guess is that if you just gave a number without the units, you're going to be losing some credit for that. All right. Predict giving your reasons whether the forward reaction is endothermic or exothermic. All right. So essentially, whether it's endothermic or exothermic has to do with the delta H. All right. Remember, that's the change in enthalpy of the reaction. All right. So we've had parts of this problem where we've calculated the delta G0. All right. And we calculated actually in this right here that we've got a negative delta G value at standard conditions. All right. Well, that means that it's going to tend to be spontaneous. All right. All right. So, all right. Well, more technically, what that means, if the delta G at standard conditions is negative, what that means is that the forward reaction, if you were to have, basically start with all reactants and no products, the forward reaction would be considered to be would be spontaneous. All right. And a quick way to rationalize that is to not only is it confirmed with the value that we got in part C, where it's a negative value. Another way would be to look at the equilibrium constant. All right, so this equilibrium constant right here is much greater than 1. All right, which means you're going to have more of the products and fewer of the reactants. All right, so what that means is that at equilibrium, it's going to be over here towards the product side. All right, and so remember, this would be like free energy over here. So remember that your standard concentrations, all right, that delta G with the little degree symbol, is at standard concentrations. It's basically saying, like, if everything had 1 molar concentration. So ask yourself, what would tend to happen if we were here, but equilibrium were here? All right, well, we would have to move, the spontaneous reaction would be to move towards the right. So the forward reaction would be favored there. All right, so we know that the forward reaction is favored here, but we know that your change in enthalpy is negative. All right, you're going from more particles to fewer particles. All right, and that part of it, so that governs this part of the equation. If it were only for this part of the equation, that would be unfavorable for the forward reaction to occur. All right, so if we know overall it's favorable, but this part of it is unfavorable, well, how does that happen? Well, the only way that can happen is if this part of the reaction right here is favorable. All right, and so remember, for this to be favorable, this has to be negative. All right, so for this overall to be negative, all right, that and this part of it right here would end up being positive. That means that this has got to be at least more negative to compensate for the positive component of that. And the reason I say that that's positive is it's going to be a negative of a negative. All right, so if that is negative right there, that means that overall it's going to be exothermic. All right, because that's what a negative delta H is. All right. Okay, in part E, they give some actual concentrations, and they say, well, if these are the starting concentrations, what would you predict the reaction direction of the reaction to be? All right, well, let's plug these things in and calculate what a Q would be. If we do that, we get a Q value as being 20.8, but we know that the equilibrium constant, so when we're at equilibrium, that value would be this right here. All right, so what that means is that this right here is actually too low. All right, so for this to be too low, that means that our numerator is too low or our denominator is too high. All right, so if we've got too low of a numerator and too high of a denominator, how do we get that back to where it wants to be? All right, we've got to move some stuff from here up to here. All right, so the reaction's got to convert this stuff down here, which is your reactants, to this stuff up here, which is your products, all right, to get that number higher. All right, so in order to do that, it's got to proceed in the forward direction. It's got to move towards the right to achieve that equilibrium. All right, so if your reaction moves to the right, that's going to increase the amount of products. It's going to decrease the amount of the reactants, and it's going to move that Q value towards that KEQ value, and that's what happens when you're going towards equilibrium. Okay, so 6a just talks about, it's a classic Le Chatelier's principle. Remember, if it's exothermic, essentially you can think of heat as being a product of the reaction, and if that's true, increasing temperature adds to the heat, and that's going to favor the reverse reaction. All right, 6b. This is one, just given the information, this has more actually to do with something we saw in the kinetics unit. Look through your reactions or equations and find the one that match what's given in the problem. It would end up being this equation right here, which would give that solution. And in the last problem, with this KEQ, that's way over 1, which means it's going to favor products, and this would be the answer.